Well, good afternoon. This is 12:22 on Wednesday, the 3rd of October, 2018. It's supposed to be Cal 3 class, and right now I'm the only one in the room. We should have started at 12:15, but I kept thinking someone was going to show up. But they haven't yet, so let's proceed with where we left off last time. Just a couple of announcements before we get going. About graduation, hopefully, if any of you are graduating this term, fall term, I hope you got your application for graduation in already, because it's awfully close to being too late to get it in. So get it in now, immediately, if you are graduating this term. If you're graduating in the spring, this is the best time to start the process for graduation, which involves getting your degree plan, updated copy of your degree plan, review that with your advisor, see what you have taken, what you're taking now, and what you have left to take, and make sure that then when in a couple of weeks we will be registering for spring term, that you get what you register for the class that you need to graduate. And if there's any that are not offered, or the two that are offered are conflicting with each other or something like that, get with the advisor, your advisor, the department chair, the instructor of the courses that are conflicting or not being offered. See if you can work something out to get what you need for spring term. If you can't, then that gives you time to do a course substitution. And that needs to be done before spring term begins. Okay? In fact, as soon as possible, so you can get it on your schedule if they approve the substitution. So get moving on those kind of things. And if you're not graduating even in spring, remember, do this. Start the process of applying for graduation the term before you expect to graduate. Don't wait till the term you're expecting to graduate. Do it the term before, so you can get all the things ironed out and in place before you get to that last term, and then find out the one course you need you can't get, so do as much as you can ahead of time. All right, secondly, they're looking for note takers. As far as I know, maybe on both campuses, I know in Birmingham they were. If you can do that, they will pay you to take notes for other students. They're also looking for tutors in the Space Centers. There's a Space Center on both campuses. I know they're looking for tutors on the Birmingham campus for math, who you would be the fantastic tutors for math, any level of math. English, computer science, biology, and Spanish, I think, are the ones they specified. We have a Space Center on this campus and Student Support Services, both of which use peer tutors. And they pay you to tutor, so please take advantage of that and tutor. Okay, the one other thing, I was going to talk about this a little later when we got closer to it, but I'm going to mention it now in case you're not here later and don't listen to the whole thing. I have your test developed, but I don't have it typed yet. So for this chapter, I was hoping to finish chapter 12 today and give you the test so you can start on it this weekend, but I didn't have time to finish typing it up. So I hope to be able to do that maybe a little bit this afternoon, and then even more so possibly a little bit tomorrow. But I'll just see. Tomorrow's iffy. If I take my class on a field trip, then I'm not going to have any time to do any typing tomorrow at all, until maybe late in the day. So we'll see. But anyway, it's not ready today. All right, those are all the announcements I can think of. I kept thinking someone was going to come in. No one has. So let's go on and pick up where we left off last time. And that was here with curvature, Chapter 12, Vector Valued Functions, 12.5, arc lengths and curvature. And we've done the arc length part. Now we're in the curvature part. Here's Theorem 12.8. The formula is for curvature. If C is a smooth curve given by R of t, that's the displacement vector or whatever you want to call it, and that defines C, that vector R of t, then the curvature K, and I think I mentioned before, most other books I've taught from call the curvature kappa, which looks like a K. It's the Greek letter for K, but they call it kappa. This book actually calls it capital K of C, of that smooth curve C. Notice it's a smooth curve, meaning it has derivatives that make sense. If they had points or bends or cusp or things like that in them, no, it wouldn't be a smooth curve. So this is a smooth curve. Then the curvature K at the point of C at the point T, the value, the parameter T, is then defined as the absolute value of the first derivative of the unit tangent vector divided by the first derivative of the displacement vector. Okay? Now, we've talked about unit tangent vector before. There's a process to go through to get there, and that can sometimes be tortuous, but it's doable most of the time. But here's an alternative formula for curvature. The first derivative of your displacement crossed your second derivative for your displacement. Okay? Take the magnitude of that vector and divide it by the magnitude of r of this first derivative of the displacement vector cubed. Okay? So, now, earlier, let me scroll back just a little bit, we had this, that the curvature was the magnitude of the first derivative of your displacement vector with respect to your arc length parameter. But remember, the arc length parameter is sometimes a very difficult thing to do, sometimes almost impossible. So it's usually you don't have the situation where you can use a formula like that. Okay? So these are the alternatives to that one. Okay, if I can get back to, there they are. Okay, the first formula implies that because r prime of t is your ds dt, that derivative of your arc length parameter, that is what your first derivative, magnitude of the, you can think of it as magnitude of the velocity vector, which is a speed, and that's your ds dt. The first formula implies that the curvature is the ratio of the change in the unit vector to the change in the arc length. Okay? The ratio of the change in the unit vector relative to the change in the arc length. Okay? To see that's reasonable, let delta t be a small number, then your t prime, your first derivative of the unit tangent vector, is a function of t, divided by ds dt, which is your speed, basically, if you think of it in that way, would be approximately, okay, your unit tangent vector evaluated at t plus delta t minus unit tangent vector divided by t. That would be delta t. That's your definition of derivative of your unit tangent vector, divided by ds dt, which is s of t plus delta t minus s of t over delta t. That's the definition of derivative of your arc length with respect to time, change of arc length with respect to time. And since the delta t's are the same, that would be t plus t evaluated at t plus delta t minus t of t, unit tangent vector at t, divided by s of t plus delta t minus s of t, and that basically is your change of unit tangent vector per change of arc length, which is exactly what we had here, okay? The magnitude of that derivative, change of unit tangent vector with respect to arc length. So I don't know why they went through all this to take you right back where we were, but that's what they did, okay? All right. Okay. Okay. In other words, for a given delta S, the greater the length of delta t, your change of the unit tangent vector, the more curvature the curve bends at t, of course, because that's the bigger change of length in your delta there. So here's an example. Here is your unit tangent vector. It's like to me they may have a little bit too much of an angle, but we'll agree that that's the unit tangent vector. And if you moved on the arc length to there, and your original unit tangent vector was there, but you know your unit tangent vector at t plus delta t is there, then the change of the unit tangent vector was there. So that's your delta t. And when the curvature is fairly sharp, and this is not, that's a fairly, reasonable delta t. But when the curvature is even sharper, like in this region, where there's your original t of t, there's your t of t moved down to this point, t plus delta t later, in other words, delta s later, and there's your new t of t plus delta t, the change of unit tangent vector is much bigger than it was here. Incredibly bigger than it was here. So the curvature is much greater where it's a tight curve than where it's a broad curve, which we've said repeatedly. So here's example 5. Finding the curvature of a space curve. Okay? Find the curvature of the curve given by r of t is equal to 2ti plus t squared j minus 1/3 t cubed k. All right. Now, since you have r, we can do the unit tangent vector if you wanted to. But since you have r, why not just do the second formula from the theorem? Let's do r prime, r double prime, and then we'll divide by r prime cubed, the magnitudes. So let's start with, let me get my pen set up. I was using the red to point with. Okay, so r prime of t would equal to what? 2i plus 2tj minus t squared k. Okay, there's your r prime. R double prime is equal to 2j minus 2t k. All right. Now, what the curvature was is the magnitude of the cross product between r prime and r double prime. So let's do that next. R prime cross r double prime would be, let's set up our I, J, K, I, J, and r prime is 2t minus t squared, 2t, and your r double prime is 0, 2, negative 2t, yeah, okay, and then repeat those 0 and 2. All right, almost got lost what I was doing there. All right, now we do like a determinant. It's not exactly a determinant, but very much like it. And this would be minus 4t squared, that's the I, that's coming this way. The j would be 0, the k would be plus 4k. And then your up diagonals would be a 0 here, Now that is a minus there with the t squared, I'm pretty sure. Yeah, it's hard to read my writing. So it's a minus 2t squared I okay. I'm going to pause just a moment here. I don't know where that 2 came from. That was supposed to be a minus. And how it became a 2, I don't know. I can't get my pen to come back. Okay. Let's start over here. A minus 4t squared I from here, 0j plus 4k. Okay? Then the up diagonals is a 0 for the k plus 2t squared I. Okay, and the reason it's plus is because the up diagonal is always negative, and one of the fronts in it was this was minus 2t squared I, but going upward, that makes a minus of that, so it's plus 2t squared I. Okay, and then the j is a plus 4tj. Okay, it was a minus 4t, but because it's an up direction, it's plus 4tj. All right, so here is this cross product. Okay, minus 2t squared I plus 4tj plus 4k. Okay. Now we need the magnitude of that. So the magnitude of this r prime cross r double prime would be the square root of 4t to the 4th plus 16t squared plus 16. Okay? All right. We can factor out a 4 out of that. That would give you 2 times the square root of t 4th plus 4t squared plus 4. And when you do that, you notice that's 2 times, that's t squared plus 2 squared. So t squared plus 2, take a square root of a square and you lose a square. So basically this gives you 2t squared plus 4. Okay, that's your magnitude. That's the numerator of your curvature. It's the magnitude of the r prime cross r double prime. Now, divided by magnitude of r cubed, r prime cubed. Okay. Now, r prime cubed. This is gonna be no, wait, I put the cube in the wrong place. R prime, magnitude of r prime cubed. The other one doesn't make any sense. Okay, so what's magnitude of r prime? That's equal to the square root of 4 plus 4t squared plus t fourth. All right, which happens to be t plus 2, just t plus 2. All right, now we're going to cube that. So here's our kappa, I'm sorry, not kappa, k, is 2t squared plus 4. Now I'm regretting that I did that. Okay, that's a t squared plus 2. Okay, now I'm going to go back and undo what I did. Let's take that 2 out of there. Okay. All right. It's 2 times t squared plus 2 divided by t squared plus 2 cubed. Okay. So this one's going to go out with one of those. So that leaves you squared. So this is 2 over t squared plus 2 squared. Okay. Now, did they say where? Okay. Find the curvature given by that. Okay. So this is going to be a function of time, or t, whatever your parameter is there. And that's exactly what, well, they did it with the unit tangent vector, which is perfectly fine too. I think this way may have been just a little bit simpler, but you come up with the same answer either way. 2 over t squared plus 2. Wait a minute. Why do I get a squared and they don't? Oh, there it is, yeah. It is there. I'm just not looking ahead. It's 2 over t squared plus 2 squared, in parentheses squared. They did it using the unit tangent vector. I did it this way, which frankly I found a little bit easier in this case. All right. Let's see how they do it, which will be using unit tangent vector. And you determine which one you like better. Okay? It's not apparent whether this parameter represents arc length, so you should use the formula, this one. Okay? Or the other one, and they chose to use this one. Your R prime, what you're going to need, is 2i plus 2tj plus t squared k, minus t squared k, which we got that too. We went on and did the second derivative too. They are not going to. So your magnitude of that would then be the square root of 4 plus 4t squared plus t to the fourth, okay, which is what we got. And if you take that out, that's going to give you t squared plus 2, because that inside the radical is a perfect square trinomial, perfect square of t squared plus 2, and so your square root of a square is just the function t squared plus 2. So there's your R prime. Now, your unit tangent vector is going to be that square, that first derivative of your R, which you have up here, this one, okay, divided by the magnitude, which you have down here. And that's just going to be just that, 2i plus 2tj minus t squared k over t squared plus 2. All right. Now what you got to do is take a derivative of that, okay? Excuse me. Now that's going to be a little bit of a messy derivative, okay? Because you got your variable in numerator and denominator. So might need quotient rule, you might need others, so let's just see if they did it right. Yes, and they are doing a quotient rule, which is low D high. Okay, if you go here, derivative of your numerator is 2j minus 2tk. Okay, so it's that denominator times 2j minus 2tk. Then it's minus low D high D low, which is derivative of your denominator. Okay, now not this denominator, that denominator is just 2t times the numerator, the high part. Okay, so this isn't so awfully bad, but it's could be worse, I guess. So your I component is going to be minus 4ti, I'm going to write that down, minus 4ti. Your j component is a t squared plus 2 times 2, so it's 2t squared plus 4. Minus 4t squared. So it's a minus 4t squared j. No. Boy. The I part was fairly easy. There's just one term, minus 4ti. The j term is a lot messier. First you have 2t squared j plus 4j minus 4t squared j. So that's going to be a minus 2t squared j plus 4. J, and then your k component is going to be minus 2t cubed minus 4t minus t squared k. Ooh. So plus a minus 2. Trying to get all the pieces in place, and it's kind of hard to keep track. Minus 2t cubed minus 4t squared plus 4j. Okay, and then we have a minus 2t k trying to make sure I don't lose a term here. It's minus no that's I knew something was really squirrely here. That's a k. I've already done my j. That's the k. Alright, that was getting me totally confused. Okay, I still don't think I have it right. I don't have all of them. Do I? Let's see. There's a minus 2t cubed k, and here is a plus 2t cubed k. So those go away. Okay? And here we have a minus, let's see, there's no t squared terms then. Plus or minus 4tk so I think that's the minus 4tk. Okay. I don't know where. I think I was getting myself completely lost here. And there's no constant term with k. I think I was getting the, wait a minute. Okay. Let's start over. I know this is a pain in the neck, but okay, the I term is minus 4ti. That's the only I term. Okay, so I'm going to sort of wipe that out. I already multiplied it by the minus 2t. Minus 4ti. Okay, the j terms. Here's going to be a plus 2t squared j, a plus 4j, a minus 4t squared j. So I think that's all up. So let's get that plus. That was 2t squared, and that's going to be a minus 4t squared, so it's a minus 2t squared j plus 4j. Okay. So the j terms are taken care of. All right, now we're going to do the k terms. Okay, here's a minus. Let me erase some of these just so I don't get confused by them. Okay, going to do the k terms. I may have had them right before, but I just couldn't tell for sure. There's going to be a minus 2t cubed k, and this is going to be a plus 2t cubed k. So those go away. These two here cancel out. They add to 0. Okay? So all we've got left is a, whoops, minus 4tk. I sure hope I got that right this time. So minus 2t cubed k and a plus 2t cubed k. So that adds a 0. It leaves you just with a minus 4t k. Okay. I think that's what I wound up with before, but I wasn't certain. Okay. Now that's your t prime of t. Okay? Now, they're using the earlier formula, so now we take the magnitude of that. And the magnitude of this is t prime of t, so the magnitude of this, and normally I put that as a unit vector, but since you're taking a derivative of it, it's not unit vector anymore, so I'm just going to leave it at thing. But the magnitude of that is going to be the square root of 16t squared, and then you got a binomial here. You're going to square that, be plus 4t fourth, That's the first one squared. Plus 16 t squared okay. All right, let's start over. Yeah, that's right. Okay. Plus 16. That's that thing squared. And then plus 16t squared. Okay. So that would be the square root of 4t to the fourth plus 48 t squared plus 16. Okay, sorry about that. My eraser's not picking up. There we go. Sorry, I seem to be losing my throat, my voice. I would factor out a 4 out of that. Square root of 4 is 2. So this would give us a 2 times the square root of t to the fourth plus, take a 4 out of that, and you're left with 12 inside here. So 12t squared plus 4. Now, that's not very it's not what they get, I don't think. Let's just see. There's a 16t squared, which is what we got, plus 4t to the fourth, which we got. Now they wound up with a, that's right. I forgot my minus sign there. This is a minus, okay? Because it's minus 8, double that is minus 16t squared. So basically these two go away, which is what I was hoping that would happen. And that just leaves us 16 t squared from there. And when you factor out the 2, that would be a 4. This gives you 4. And that, again, is 2 times t squared plus 16. That's not right. No. I don't know where my head is today. T squared plus 2. That's it. Same as we had before. All right. Now, two over that's your, okay, sorry about this. All right, that was all your numerator. All this is over your denominator, which is t squared plus 2 squared. So one of these goes out and leaves you just 2 over t squared plus 2. All right, that's done now. There is your magnitude of the unit tangent, first root of the unit tangent vector, okay? And then we already had from before, which I've already erased, I think. Yeah. Well, they have it here. Magnitude of r prime, which is t plus 2, t squared plus 2. So when you put that in your denominator underneath this, you get 2 over t squared plus 2 squared. Okay. Which is the same thing we got. Frankly, I think the way we did it was a little bit easier. Now, it may not always be, but it should be a little bit easier. So let's go back and pick up from where they did. That's your t prime, which is just like what we got, minus 4ti plus 4 minus 2t squared j minus 4tk over t plus 2 squared, t squared plus 2 squared. The magnitude of that is then going to be that numerator under a square root, you know, squaring the components and adding them together. And for some reason, I've suddenly gotten very cold. But that's what we did. And it's over your denominators squared. Now, wait a minute. Let's see. You would square that denominator and then take a square root of it. So that's why it comes out as a t squared plus 2 squared in the denominator. Okay, and then when we simplify terms there, which I hope you see, these two add to 0, then that simply gives us 2 times t squared plus 2 in the numerator over t squared plus 2 squared in the denominator, which is just 2 over t squared plus 2. But then when we divide that by magnitude of r prime, which was you know, you get exactly what we did, 2 over t squared plus 2 squared. Okay, and that is your curvature at any time t. And that's all they were asking for. They weren't asking for any specific one at any specific time. They just said that no. Yeah, that was example 5. I turned the page for some reason. Here's here's theorem 12.9. Curvature in rectangular coordinates. Okay? If C is the graph of a twice differentiable function given by y is equal f of x, y is equal f of x, okay, then the curvature k at a point xy if C is the graph of a twice differentiable function given by y is equal f of x, okay, so you have some curve. Now they don't say f of x, y, and z, f of x, so x is now your, indicate this is a plane curve, y is equal f of x. Then the curvature k at the point xy is the magnitude of y double prime divided by 1 plus y prime squared raised to the 3/2 power. Okay, now that just kind of came out of the blue. Okay, they didn't lead up to that very well at all. You've gone now to a function curve, not a parametric curve, and you just have to say, yeah, okay, we buy that. Okay, that's all they give you the opportunity to do. Okay, and I was trying to rationalize some way to deal with this, and I, for the life of me, well, I kind of can in a small way. But it's not worth, I don't think, the time to try to do it. Just, that's what it is, okay? Y is a twice differentiable function. C is the curve, that's the graph of that twice differentiable function. Then the curvature at any point xy is your y double prime divided by 1 plus y prime squared to the 3/2 power. Okay, and they do in their proof a little bit of a rationale for that. You can say that that displacement vector is xi plus alpha of xj plus 0k. X is the parameter. You can obtain r prime of x then by just taking derivative of it, I plus f prime of j. Okay, then that's your derivative, okay? And your magnitude of that derivative would then be your 1 plus f prime, or y prime, they're calling it here, squared, which you see in that denominator, okay? And r double prime is the second derivative of f, because when you take the I guess I'll be writing this down. Okay, here's your vector. And now it's a function of x, okay? Like I said, that's now your parameter here. This r of x is equal to xi, and now xi, okay, because that's your x value. Now this isn't this point x, this is your variable x, plus f of xj, which is your y value j. And you don't have a k component, okay? This is a plane curve, okay? 0k. All right. So then your r prime of x is equal to I plus f prime of x j, okay? And then your magnitude of your r prime of x is equal to the square root of 1 plus f prime squared. And we can put the dx, no. Okay, just leave that, that's it for right now. Okay. Yeah. All right. Okay. Now, what they do, they're going to do it the same way we did before. Okay. Not going through the unit tangent vector, but doing your r double prime of x is going to be f double prime of x. Okay. J. Okay, you take derivative of 1 is 0 and derivative of f prime is f double prime. Now I don't think we need that one, but what we do need, God, that's scratching my eye itches, is your cross product between these two. So it's going to be I, J, K, I, J, and that's going to be 1 Seems like there should be an easier way to do this, but this is how they sort of skip this step. They just say it is, but let's go on and do it. This is your F prime, and of course K is 0, so you put a 1 and an F prime again, and then your R double prime is a 0, F double prime, 0, 0, F double prime. Okay? Then when you do your matrix type stuff, that term's a 0, that term's a 0, that term's a 0, that term's a 0. Whoa. Not true. Oh, that's it. I didn't do that one. Okay, I thought. Everything's turning up 0 except the third one, okay, which is going to be F double prime. So the cross product here, R prime cross R double prime, is equal to F double prime K. And if you want the magnitude of that, it's just F double prime. R prime cross R double prime. That would just be F double prime. Okay, that's what they came up with. Did you need that? Yeah, you needed that. So that then gives you Y double prime, magnitude or absolute value of Y double prime divided by the R prime cubed. Okay? Okay. And this, okay. Here is your magnitude of R prime. And when you cube that, you get this thing right here. When you cube this, that becomes 1 plus F prime, or let's call it Y prime, squared to the 3/2 power. Okay? So that's where that comes from. So your numerator came from here, that's Y double prime, and your denominator. So that's why the curvature is that. Okay. Now, let's move on. This is the paragraph underneath that proof. Let C be a curve with curvature K at point P. The circle passing through the point P with a radius 1 over K is called the circle of curvature, okay? Where the circle lies on the concave side of the curve and shares a common tangent with the curve at the point P. The radius is called the radius of curvature at P, and the center of the circle is called the center of curvature. Okay. Seems like there's another name for that circle of curvature. I can't recall what it is now. Other texts have used that. Circle of curvature sounds perfectly fine to me, but it seems like there is another one that they use. They say here then that the circle of curvature gives you a nice way to estimate the kappa, keep saying kappa, K, curvature K, at a point P on a curve graphically. Using a compass, you can sketch a circle that lies against the concave side of the curve at point P, and the circle has a radius, call it R, okay. If the circle has a radius R, then you can estimate the curvature to be K is equal to 1 over R. So that just tells you a way to estimate this. So let's see if they do example 6. Not yet. Oh, I'm sorry. This is the paragraph I just read. I didn't know they were going to do it again. The circular curvature gives you a nice way to estimate the curvature K at point P on the curve graphically. Using a compass, you can sketch a circle that lies against the concave side of the curve at point P. Okay? Now, the key here is to find the radius that works best. It makes it sound real easy. You just get a compass and do it. Well, they showed that they made a pretty good estimate here. If the circle has a radius r, whatever that turned out to be, then you can estimate the curvature to be K is equal to 1 over R at that point. Okay, so that's just an estimation process. Okay, let's see if they do example 6. Yes, they do. Find the curvature of a parabola given by y is equal to x minus 1/4 x squared. I just realized something I forgot to do. Okay. 55. Okay. Just keeping up. Okay. X minus 1/4 x squared at x equal 2. Find the curvature at that point and sketch the circle of curvature at 2, 1. Now, what they're assuming there, and I think it's a good thing to check, when x is equal to 2, y is equal to 2 minus 1/4 of 2 squared, okay, which would be 2 minus 1/4 of 4, which would be 2 minus 1, which is 1. So sure enough, that is your y value. So make sure you're on the right place, and you are, okay? So find the curvature of the parabola given by that curve, okay? Now, this basically is using the theorem we just did, and if you follow what's happening with that, your y prime would then be, from this up here, minus 1/2 x, right? 2 times minus 1/4 is 1/2, negative 1/2 x. Your y double prime is going to be minus 1/2. Okay, and that's what we need in the numerator. Okay, what we need in the denominator, or what we need in the numerator is absolute value. Well, absolute value of y. Yuck. Okay, so hard to read. Absolute value of y double prime, which would be 1/2. Okay. And your denominator, if you recall, is 1 plus y prime squared to the 3/2 power. Okay? Well, we got our y prime, so 1 plus the y prime squared would be 1/4 x squared. Okay? Which is very close to what we had up there, but not the same. Okay? And we're going to take that and cube it. Raise it to the 3/2 power. Okay? Okay. Now, so your curvature is that ratio, 1/2 over 1 plus 1/4 x squared to the 3/2 power. Okay, if I'm remembering correctly, I think that is. Okay. Now we want this when x is equal to 2. So this is going to be 1/2 over 1 plus 1/4 of 4 to the 3/2 power. Okay, which will be 1/2 over 1/4 of 4 is 1. 1 plus 1 is 2. 2 cubed is 8. So it's the square root of 8, which is 2 root 2. Okay, so this is going to be 1 over 4 root 2. My calculation's right. No, it's not. Okay. Y prime is 1 plus, oh goodness gracious, I left off my 1 here. Derivative of y is 1 plus, yeah, I thought I had it in there. Okay, so we got some changing to do. Sorry about this. I was saying, why is this coming out so strangely? All right, let's wipe all this out and start over again. Sorry about this. This something, my head's not right today. I don't know why. Well, I know a little bit of something, but I woke up very, very early this morning and couldn't go back to sleep, so maybe that's what it is, sleep deprivation. All right, so y prime squared, okay, would be 1 minus x plus 1/4 x squared. Make sure I did that right. If you're squaring this binomial, square the first, twice the product of the two, that would be a minus x plus the square of the last, which is that. Okay. And then 1 plus that, 1 plus y prime squared would be 2 minus x plus 1/4 x squared. Okay? Okay? And then this thing, we're going to raise to the 3/2 power. Okay. So now your kappa is your y double prime, or the magnitude of that, 1/2 over this thing. 2 minus x plus 1/4 x squared to the 3/2 power. And this is where we plug in the x equal 2. So it'd be 1/2 over 2 minus 2, which of course is 0, plus 1/2, so that's just a 1, isn't it? 2 squared is 4 and 1/4 of that. So it's 1 and 1 to the 3/2 power is still 1, so this is 1/2. Okay. There's your curvature. K is 1/2. Okay. And at that point P, which is 2, 1, that is going to be your curvature is 1/2. So the center of curvature they sort of, oh yeah, okay. Yeah. Since the curvature is 1/2, the radius of curvature there is 2. So the center of curvature, now here's where they kind of, you almost have to have the graph to do this at this point. And they did draw the graph. And the thing about the graph is that you see it is a parabola, and this 2, 1 happens to be the vertex of the parabola. Okay, it's concave down, it's bending downwards, and you almost have to graph it to prove to yourself that's true. But at x equal 2, y is equal to 1, we'd already done that. If you go back to x equals 0, of course, y is equal to 0, so it's going to cross the x-axis there. You go out to 4, 4 minus, and then 4 squared is 16, and 1/4 of 16 is 4, so that's going to be 0. That lets you know this is indeed the vertex, okay? Now, I didn't graph it. They're going to graph it on the next page. In fact, let's just move on, well, on the next slide. So let's go on and take this off, okay? And the curvature at x equal 2 is as follows. You did y prime, which is 1 minus x over 2. I forgot to do my 1. And y double prime, no, y prime, oh, okay. At x equal 2, y prime is 1 minus x over 2. When x equal 2, that's 1 minus 1, which is 0. So that's the other thing that tells you this is the vertex of the parabola. The parabola is opening downward with 2, 1 being the vertex. Y double prime is minus 1/2, so y double prime is minus 1/2. I don't know why they wrote it the second time. Here they took the second derivative. Here they just identifying that is the second derivative at that point x equal 2. So basically this is at any x, this is at x equal 2. Okay? So, now, the kappa is then the absolute value of your second derivative, which is 1/2, divided by 1, which is just 0. So it's a lot easier than plugging in all the way. Okay. Because the curvature there is 2, it follows that the radius of curvature is the curvature is 1/2. It follows that the radius of curvature at that point is 2. And since that is the vertex of a circle, that radius of 2 is directly below that point. So that would be at 2, -1. Okay? And that's what this shows here. Okay? So the center of curvature is at 2, -1. We didn't have to do all this. All they said was, oh yeah. Then they said sketch the circle of curvature at 2, 1. So you did need this. So the circle of curvature at 2, 1, okay, I guess I'll do it in dark. Let's just imagine a new axis here just for drawing the circle. Radius of 2, so you're going to go out from here to 4, here to 0, and down here to -3. Okay, and there's your circle of curvature for that parabola. So you see it's a very nice fit there. Okay. And because this is where the parabola bends the strongest, is at the vertex, that's going to be the largest curvature you've got, 1/2. Everything else from here on, and they make a suggestion to you, try doing it at 4, 0, which is this point over here, and if you do the curvature there, you'll see it's going to be much, much less. That curve would be a curve that has a huge circle of radius, meaning the curvature is much, much less. All right. I think that's all we had to do on that. And the figure note the curvature as greatest curvature at P. All right. Now, the little verbiage they say here, arc length and curvature are closely related to tangential and normal components of acceleration. The tangential component of acceleration is the rate at which change of speed, which in turn is the rate of change in arc length, and that component is negative as the moving object slows down, positive as it speeds up, regardless of whether the object is turning or traveling in a straight line. So the tangential component is solely a function of the arc length and is independent of the curvature. On the other hand, the normal component of acceleration is a function of both speed and curvature, and that component measures the acceleration acting perpendicular to the direction of motion. To see why the normal component is affected by both speed and curvature, imagine you're driving a car around a turn, and I don't know if they have, I don't think they have this figure. I don't think they do. So you'll have to look in your book to see. I can't draw that well anyway. When your speed is high and the turn is sharp, you feel yourself thrown against the car door. By lowering your speed or by taking a more gentle turn, you're able to lessen the sideways thrust. And then this theorem follows from that. If R of t is the position vector for a smooth curve C, then the acceleration vector is the second derivative of that R of t, but it's also your tangential component is your change of your speed, okay, strictly depending on speed, and then the normal component is so that would be the time rate of change of speed, whereas the normal component is your curvature times the speed squared, okay. So the first is the second derivative of speed, and the second, the normal, that's the tangential component, and your normal component would be your curvature times your speed squared, where k is the curvature at C and ds dt is the speed. Okay. Now, here we go to do that. Find the a of t and a sub t and a sub n for the curve given by this. Okay. All right. Well, you certainly need r prime of t. No way around that. And that would be 2I plus 2tj minus t squared k. Okay? One thing you got to do is that. Okay. Now, what do we do with that? Well, remember we want the speed, which is the magnitude of this. So the magnitude of this, which we're going to call our ds dt, that is your speed. S meaning arc length, not speed. Okay, arc length. Don't let that confuse you. That's equal to the magnitude of your r prime of t, which is the square root of 4 plus 4t squared plus t to the fourth. Seen this before, haven't we? Okay. Which is t squared plus 2. Because this is a perfect square of t squared plus 2 squared, and the square root loses one of those. So there is your speed, magnitude of the velocity. Okay. Now, we need our curvature. Okay. And this is because it is the one we did back on example 5. That's the function. No reason to go back and recreate the wheel, okay? From example 5, we know the curvature, K, was at 2 over t squared plus 2 squared, okay? Now, the a sub t then, tangential component of your acceleration, okay? That's going to be the first derivative of your speed, which is second derivative of this. So d2s dt squared is going to be 2t. Okay? So that is going to be 2t. Now, did they give us? No, just, okay. Now, your a sub n is going to be kappa, or k, times ds dt squared. And your k is 2 times t squared plus 2 squared times your ds dt, which is squared, which is t squared plus 2 squared, and that's equal to 2. Okay? Wow. So there you found your a sub t and your a sub n. A sub t is 2t and a sub n is simply 2, the normal component. Now, are we to do anything with that? I guess not yet. Okay? With no one in the room, I'm sort of a little weird about going over it. So let's back off and see how they did it. That's how we did it. Let's see how they did. Okay, from example 5, you know that ds dt is equal to t squared plus 2, and your kappa was 2 over t squared plus 2 quantity squared. So your tangential component of your acceleration is the first derivative of your ds dt, which would be 2t. Okay? Your normal component of your tangential of your acceleration is kappa, I'm sorry, I keep saying kappa, k times ds dt squared, where your ds dt squared is t plus 2 squared, and your k is 2 over t plus 2, t squared plus 2 squared. So it leaves you 2 over t squared plus 2 squared times t squared plus 2 squared is simply 2. Normal component is that. So here's the application. There may be many applications in physics and engineering dynamics that involve relationships among speed, arc length, curvature, acceleration. One such application concerns frictional force. A moving object with mass m is in contact with a stationary object. The total force required to produce an acceleration a along a given path is F equal ma. Newton's second law. Okay? Now, the mass times the acceleration, there's two components of the acceleration. There's the tangential component, which is t2s dt squared, and that would be times your tangential unit vector in the tangential direction. Unit tangentials. The tangent vector, unit tangent vector, goodness, I can't say it, plus m, the mass, times the normal component of your acceleration, which is k times ds dt squared, times the normal, unit normal vector. So this will be ma. Why didn't they say this in the first place and then do the other? I don't know. That would have made a lot more sense. A tangential component in the times the unit tangent vector plus ma, the normal component of your acceleration vector, times the unit normal vector. The portion of this total force that is supplied by the stationary object is called the force of friction. That's what holds it in place as you turn. For example, when a car is moving with a constant speed that is rounding a curve, a turn, the roadway exerts a frictional force that keeps the car from sliding off the road. If the car is not sliding, the frictional force is perpendicular to the direction of motion and has a magnitude equal to the normal component of the acceleration. Okay, let's read that again. If the car is not sliding, the frictional force is perpendicular to the direction of motion. Okay, pushing you toward the center of the circle. Okay, and has a magnitude equal to the normal component of the acceleration. Normal component, yeah. Yeah, not tangential, normal. Okay, as shown in this figure. The potential friction force of the road around a turn can be increased by banking the roadway, which we know. Okay. So, I think I'm going back to my red. That seemed to be a better pointer than the black. Okay. If I can get to it. Okay. Car going around the curve. This tangential component of the acceleration, of course, is tangent to the curve. The normal component of the force and the acceleration and everything else is toward the center of the curvature. Okay, and these are perpendicular to each other. Tangential toward the center. The force for friction is what is pushing this car inward. Okay, if the road is flat, the force of friction has to be doing it all. What they're saying is the potential frictional force of a roadway can be increased by banking the roadway. Not quite true. That is now you have part of the weight of the car pushing you inward because you have a component from the banking of the road that is pushing you inward. Okay. Another way to express that is the normal from the surface of the road, which we haven't really talked about, but that's going perpendicular to the road, but that's now tilted. If you bank the road, that's tilted to the center. So there is a component of the force that you actually do get out of the car, you know, because of the banking, you know, of it. So I don't really quite like the way they worded that. It's not the frictional force. So here's example 8. Okay, a 360 kilogram go-kart. Okay, not a car, but a go-kart, is driven at a speed of 60 kilometers per hour around a circular racetrack of radius 12 meters, as shown in this figure. To keep the cart from skidding off course, what frictional force must the track surface exert on the tires? Okay. All right, we've got several things we're going to have to do here. One is a unit issue, and I don't know how much they're going to get involved with that. Let's see what we can do without the unit issue. A 360 kilogram go-kart is driven at a speed of 60 kilometers per hour around the circular racetrack of radius 12 meters. To keep the cart from skidding off course, what frictional force must the track exert on the tires? Okay. Now, constant speed 60 kilometers per hour, that means there is no tangential component of your acceleration. All your component of your acceleration is normal, okay? So that frictional force is your normal force here, okay? And it's going to be related to that acceleration. Now, radius of 12 meters, what that tells you, your K is going to be 1/12. Your curvature is 1/r, because it's a circular track. Okay? The speed is 60 kilometers per hour, so your speed squared would be 3,600. Now these are weird units. Kilometers squared per hour squared. Okay? The units for this curvature is per meter. Okay? Now, we haven't gotten into very much dimensional analysis, but that's really what it is. 1/, and we didn't want to mention curvature, we weren't mentioning any units at all. But in this problem, it has that. So you see, we do have an issue here of kilometers squared and meters. So we got to solve that dilemma. Okay. Now, usually your force is in newtons, and a newton is a kilogram meter per second squared. So another reason, we've got to deal with your speed. So rather than squaring that, it's so much simpler to deal with your speed first, get it in meters per second, because that's what you need, and go from there. So 60 kilometers per hour, multiply that. Now, you don't have to do it this way, but this is the way I find easiest and best. And you're trying to get to meters per second. Now, I'm going to do it fairly quickly because we're almost out of time. It doesn't matter which one you do first. If you change your kilometers to meters, okay, then put kilometers down here and meters up. You put two blanks here. One's for numbers, one for units. Always put the units in their place. So kilometer here, meters here. And then you match the units. 1,000 meters is 1 kilometer. Okay, so that wipes out your kilometers. Over here, put your hours in the numerator and seconds in the denominator. Now, I'm cheating a little bit here. 1 hour is 3,600 seconds, because there's 60 seconds in a minute and 60 minutes in an hour, so it's 60 squared, which is 3,600 seconds. So this would give you, okay, now let's take this 60 here and divide it into 3,600 here, and that gives you 60, right? That's how we got it. And then you can lose a 0 here, and this gives you 50/3. 50 thirds of a meter per second. And you can give that a decimal number if you want to. That's the one that we need to square. So the speed squared, and I'll just call it ds dt squared, would then be 2,500 over 9. Okay. Now, take that, okay, and multiply it by your kappa. I'm sorry, I keep calling it kappa. K. So multiply that by 1/12. Okay. Now, I know that 4 will go into 12 3 times, and 4 will go into this 625. Yeah, 625. So we got, that's So this is 625 over 27 is your A sub n. All right. Multiply by your mass, which is 360 kilograms. Okay. And I haven't kept up with the units, but I think they'll work out here. And I don't have a calculator on me. So let's see what they got. I know that 9 will go into this 3 times, 9 will go into that 40 times. So we got some number 25,000 over 3 is what I get it to me. Let's see what they do. Frictional force must equal the mass times the normal component of acceleration. Circular path of curvature is 1 over 12. We got it. Frictional force is the mass times K times speed squared. And, yep, boy, 360 kilograms times 1 over 12 times, they even were worse than me, 60,000 meters per 3,600 seconds squared. And they get about 8,333 kilogram meter per second, which is, by the way, a Newton. Okay. And I think that's where we were heading to. I just ran out of time. So the last slide is going to be the summary slide here. We didn't quite finish today, so I don't feel quite as bad. I still wish I had gotten your test ready to give you, but I didn't. I've got it ready, but not typed, so I don't have to do that, hopefully today or tomorrow. Or I don't have much time on Friday or opportunity either. But anyway, homework exercises here. I think you can do any of the odds 3 through 7. They're all at calcchat.com. You can do number 9. That's at calcchat.com. Any of the odds 11 through 15, they're all at calcchat. 13's at calcview. You can do 17 is at calcchat. 19 or 21, either one or both, and they're both at calcchat. 21's at calcview. Any of the odds 23 to 27, they're all at calcchat. Any of the odds 29 through 35, they're all at calcchat. 33's at calcview. Either 37 or 39, they're both at calcchat. Any of the odds 41 to 47, they're all at calcchat. 43's at calcview. Any of the odds 49 to 53, they're all at calcchat. And then either 55 or 57, they're both at calcchat. There is an exploring concepts thing at 59. If you can find it there, it should be at calcchat. There's an investigation one that requires some graphing utility, it looks like. 63 and or 61 and or 63 and or 65 and or 67. So any of the odds 61 through, let's just carry it all the way to 71. Any of those that you choose to, they're all at calcchat, or should be. 73 should also be at calcchat. Then there's a proof of 75. You can try that if you'd like. And then some other odd problems, 77 through 81. All of those should be at calcchat. 83 and 85 are true-false. They should be at calcchat. And then there's some Kepler's laws of planetary motion. They give goodness gracious, do they even give it to you? Yeah, okay, I guess everything you need is here. Any of the odds 87 through 93. Okay, now, problem is some of what you'll need are in some of the even problems, so you'll have to just look at those. Then, if you want to get ready for your test, the review exercises, again, the odd numbers are at calcchat. I think all the answers are in the back of the book, but only odd numbers are at calcchat. So you can do 1 or 3 if you want to, 5 if you want to, 7 if you want to, either 9 or 11 if you want to, 13, 15, 17, 19, 21, 23, 25, either 27 or 29, either 31 or 33, or both if you choose, 35, either 37 or 39 or both, 41, 43, 45, either 47 or 49, 51, 53, either 55 or 57, 59 or 61, 63 or 65, 67, either 69 or 71, and finally 73. Okay, we will pick up next time. We'll finish 12.7. I'll give you your test, knock on wood, and then we'll get started on 13. All right, we'll go from there. Good deal. Hope you have a good weekend. Start getting ready for the test. I'll try to have it ready on Monday.